Welcome to this session on pushover analysis simplified with advanced design. First, we will go through the concept of the pushover analysis. Then we will see the three major steps of this analysis, which are the pre-analysis, the analysis, and post-analysis. First, let's start with the concept. Pushover is a static nonlinear analysis in which the structure is pushed by a monotonically increasing load pattern until a displacement that satisfies the seismic demands of the structure. So, in other words, what do we do here? We have a structure. On this structure, we adopt a load pattern that represents the seismic forces applied on the structure. So, step by step, we increase this load pattern. Of course, the proportions of the loads are always respected in load pattern, so we always respect this shape of forces adopted from the beginning. We keep increasing the load step by step on the structure, and we monitor the displacement of the structure. So, what we record at each step is the total base shear of the structure and the displacement of a certain point on the structure. We will get back to which point we consider on this structure. So we record the base shear versus the displacement of this special point that we call control node, and we plot this step by step. We get what we call the pushover curve, which represents the lateral resistance of the structure. Now, pushover analysis is a performance-based design approach. What do we mean by this? Previously, in classical analysis, what we do is a strength-based design. So, previously, we work in the elastic domain. We calculate the internal forces due to earthquake, and then we design the structure according to these internal forces. However, in most of the cases when we have seismic action on the structure, we have nonlinear material behavior, we have plastic hinges occurring in the structure. So, in order to be able to do this in a simple way in classical analysis, what we do is that we take into account this plastic nonlinear behavior by applying a simple reduction factor on the load applied on the structure. So instead of going into nonlinear analysis, into plasticity, what we do is that instead of having the full load applied on the structure in the elastic domain, since we know that the structure cannot go to this far in loading because it has a limit, it has the elastic limit. Once this limit is reached, we will have plasticization in the structure. So we apply a certain reduction factor on the load applied on the structure. In this way, we can stay in the elastic domain of calculation, and this is easier for calculation. The problem with this approach is that the reduction factor, also known as behavior coefficient, is defined by the codes according to the type of structures, and generally this factor is the same for the entire structure, which does not reflect the true case. In reality, each structural member will have its own reduction coefficient. So, in this, what was previously called as strength-based design, this is what we do. Now, with the pushover, it is a performance-based design. In pushover, we go into the nonlinear domain. We do nonlinear calculation. We know that our internal forces are capped at a certain limit, which is the elastic limit. Now, what interests us in the design is that how far does the structure exhibit plastic deformation? So this becomes the design criteria. The performance of the structure is now the performance, is the base of the design. From here comes the name performance-based design. So in the performance-based design, we are interested by how far we have plasticity in the structure. This depends, of course, on the type of the structure. If the structure needs to remain operational or to have a little damage after the earthquake, if this is an important structure like hospital, fire stations, etc., in this case, we design to have a little to no plastic deformations during earthquakes. So we have strict limitation that we can see over here, for example. Now, if the structure is a little bit less important, we allow a little bit more plasticization. We have this limit state that we defined by seismic codes. If the structure is not important, we have what we call near collapse, or collapse prevention according to FEMA code, or near collapse according to Eurocode. In this case, we allow more plasticization in the structure. So the purpose in performance-based design approach is that we are interested in monitoring how far the structure exhibits plastic deformation, and if this plastic deformation respects the limits placed by the codes according to the structural use and importance. So what is the purpose of the pushover analysis? The purpose of the pushover analysis is to see where plastic hinges will form inside of the structure, how far plastic deformation will be exhibited in these hinges, check if the degree of plasticization occurring inside of the structure respects the limit states defined by seismic codes for this importance of the structure, for the proper use of this structure, and then if we need to do some structural adjustments, in this case we can do it. Also, pushover analysis serves to verify the structural behavior coefficient, because as we said earlier, when this factor is used in classic approaches, it is single one for the entire structure. It is an approximation. Now with pushover analysis, we can verify it. As we can see here in the example, using pushover analysis, we can identify where plastic hinges will form. Generally, we prefer plastic hinges to occur inside the beams, not the columns. We prefer to have what we call strong column, weak beams. So if plastic hinges occur in the beam, as we see in this structure, the structure will remain relatively stable. Whereas if plastic hinges form in the columns, we will have what we see here as what we call here as a soft story, which will lead to the collapse of the structure. So pushover analysis is an important tool in identifying where plastic hinges will form in the structure. Next, we will see how to use pushover analysis in advanced design. Three major steps are required to conduct a proper pushover analysis. First, we have the pre-analysis, where input is made on the model. Then we have the analysis, where calculations are made. And finally, we have the post-analysis, in which results interpretation are carried out. Now let's focus on the pre-analysis input phase. Here we need to define first the lateral load pattern to apply on the structure, and two, the plastic hinges location and characteristics. As we said, during pushover analysis, seismic loads are presented by a horizontal load pattern that is increased monotonically on the structure. This load pattern is defined by seismic codes. The shape of it can be proportional to the first mode shape, can be uniform, can be triangular, or can be parabolic. This depends on the period of vibration of the structure, and also it depends on the seismic code in use. For example, the Eurocode requires to do two pushover analysis simultaneously, one with the uniform load distribution and the other proportional to the first mode shape in the considered study direction. Now, after defining the load pattern on the structure, we need to define where we might have nonlinear behavior in the structure. Because if we give the potential to any structural element to have the potential of undergoing nonlinear material deformation, this would require an enormous calculation time in the model. To be realistic, we know that nonlinear deformations will occur in the most stress zones inside of the structure. So let's say if we have a frame structure which is subjected to horizontal seismic loads, the most stress zones in this structure will be where we have the highest bending moment. In this case, this will be the beam and column extremities in bottom lower floors. So we place the nonlinear plastic hinges, the potential to undergo nonlinear deformation, in these zones. Also, when we have a structure with bracing elements, these bracing elements are the most susceptible to undergo nonlinear deformation, so we place actual hinges in them. How we model these hinges? These hinges are modeled as nonlinear springs inside of the structure. Now, how we determine the behavior of these nonlinear springs? Generally, the behavior of these nonlinear springs is determined by seismic codes, taking into account the section dimensions and the reinforcement in the section. For example, for concrete elements, we have the FEMA code, in which here we have the behavior curve, the characteristic curve of the nonlinear spring. We have first the elastic part, then we have the plastic part, then we have strength loss, then we have some residual strength, and then we have total strength loss. In the Eurocode, we have elastic part and plastic part. And the codes define on these curves the plastic limits that we talked about earlier, the plastic limits that I need to control, I need to verify in the structure if I allow a little plasticity, medium plasticity, or I allow a lot of plasticity depending on the importance of the structure. We can see it here in FEMA, for example, as immediate occupancy, life safety, collapse prevention. Here we have what we call damage limitations, significant damage, and near collapse. Let's consider this structure made of steel beams and columns. On this structure, we have dead load case, we have live load case, we have the classic model spectral earthquake analysis, and we have also defined the pushover load case. We can see in the property list of the pushover load case that we have two load types, load type 1 and load type 2. These are for the two parallel pushover analysis required for Eurocode. In this example, we will not do two pushover analysis. We will only do one. This is why we have enabled this one and disabled this one. We can also select in which direction we want to study the pushover. We can do it in X plus, Y plus, X minus, Y minus, we choose. In our case, we choose we only just want to have it in the X plus direction. Now we need to define the load pattern distribution. So we need to define the load pattern according to which the horizontal forces will be increased on the structure. We have many options for the load pattern in advanced design. We have concentrated load on the top of the structure, we have a uniform distribution, triangular distribution, parabolic distribution, and user-defined distribution. In our case, for this example, we will consider a user-defined load distribution. Now, since we have selected a user-defined load distribution, we need to assign horizontal loads on the structure. So we do this, we place horizontal loads, as we can see here, we place some horizontal loads on the structure. These are the pushover horizontal loads that are user-defined. These loads will be incremented progressively, will be increased progressively during each load step, while respecting this distribution, this load pattern that we have here. Now, after defining the load pattern distribution of the horizontal loads on the structure, we need to define the location and the properties of the plastic hinges. To do so, we select an element. We see here that in this element, it's a steel beam. We see here that we have plastic hinges, we have extremity 1 and extremity 2. Here we define the plastic hinges properties at extremity 1 and extremity 2. The eccentricity here refers to the distance from the extremity where the hinge is placed. Generally, the plastic hinge is not placed directly on the extremity. This will cause model calculation problems. So for this reason, we have always small eccentricity, a small distance between the extremity and where the hinge is applied. Here, the user might choose this distance. In this case, it is 0.25 meter away from the extremity. The plastic hinges could work in bending on local axis Y or local axis Z, or it can be an actual hinge that works in traction and compression along TX, as we see here. In our case, we want plastic hinges and we want them to work in both major bending and minor bending axis. So we activated these two. Similarly to extremity 2, we did the same thing. Now for each extremity, if we want to see the properties of the plastic hinge, we click here. Okay, and here we see what we have. We can use auto-defined, so to be defined by the code, the properties, the characteristic curve of the hinge, or user-defined if the user wants to enter it by himself, the behavior curves, characteristic curve. So for the auto-defined, we have the option to use the Eurocode or the FEMA. As we can see here, this is a representation of the characteristic curve of the plastic hinge, and if the user chooses by himself user-defined, he can modify manually these values as we see here. For our case, in this example, we will stick to auto-defined, defined by the code. And this is along y-axis and here along z-axis also. By clicking here, we switch from y and z. So this definition was made for all structural elements in this example. Since this model is not very big, we can do for all structural elements in this model. Second major step for a proper pushover is the analysis. Here we calculate the pushover curve. After defining the load pattern to represent the horizontal load on the structure, and after placing the plastic hinges inside of the structure, now we start step by step to increase the horizontal load applied on the structure while always respecting the load pattern distribution. At each step, we monitor the displacement occurring on the structure. Generally, we monitor the displacement of a node that we call control node. In most cases, this control node is chosen to be on the top level of the structure. So at each load step, we have the total applied horizontal force on the structure, the displacement of the control node. We can plot the base shear, which is the total horizontal force applied on the structure, versus the control node displacement. Step by step, we connect the dots and we get what we call the pushover curve. Generally, we keep pushing the structure until reaching a certain preset base shear value, or until we have a collapse of the structure. In this way, we stop the analysis. We cannot go any further. Now, the pushover curve represents the structural capacity in resisting lateral forces. Now, after choosing the load pattern and defining the location and the behavior of the plastic hinges, we need to set up parameters for the nonlinear calculation of the pushover curve. First, we go here to the pushover case in x direction. As we said, to obtain the pushover curve, we need to monitor the horizontal displacement of the structure. So we need to choose a control node. Here we choose the control node. We put the number of the control node. In this case, we choose this node over here. Okay. Then we need to set a limit for the horizontal forces so that advanced design will keep pushing the structure until reaching this limit or reaching the failure. But in our case, because we selected user-defined load pattern, so advanced design will keep pushing the structure until reaching the pattern that we defined over here. So we'll keep pushing the structure until reaching these values that we defined over here. But in other cases, we have the option to keep pushing the structure until reaching a certain base shear equal to a percentage of the total gravity loads applied on the structure, or we can directly set the target value of the base shear to reach. After doing this, we need to check the parameters of the nonlinear calculation. Here in the nonlinear calculation, we have the option to disable or enable large displacement analysis. Also here we see the parameters for the classical Newton-Raphson nonlinear analysis. Here we will keep default parameters for the Newton-Raphson analysis, nonlinear analysis. And here we have the option to start the pushover analysis after certain loads have been applied on the structure. So you can, for example, apply initially the gravity loads on the structure, and once these gravity loads are applied on the structure, you can start pushing the structure horizontally after this. You can choose which load case or combination to apply initially before starting the pushover. For this example, we will not do this. We will consider applying pushover directly on the structure. Okay, so now we're ready to run the analysis. We go here, and we go to pushover calculation. We can clearly see that once this has been enabled, also it enables steel calculation and reinforced concrete calculation. This is because in order to determine the behavior of the plastic hinges, advanced design need to know for reinforced concrete section the reinforcements that we have in the section, and for steel sections the class of the section. Here in our case we are using steel sections. We have already defined the steel section. We don't need to run a steel calculation to define these sections. We already did them because the focus now is only on pushover analysis, so we have the option not to activate them if the needed information is already provided. So we can run the analysis. Of course, this analysis will take a little bit longer than a classical analysis because advanced design is conducting a nonlinear Newton-Raphson analysis. So it divides the load to number of steps, and at each step it increments the load, and then during each step we have nonlinear calculation that includes multiple iterations that needs to converge. Once this converge, advanced design will pass on the next load step, and so on until we get the results. So here now, once we have the results, we can click here and we can see that we have the pushover curve of the structure. This is the base shear versus the displacement of the control node. Also, we can see if we want to see, for example, the displacement due to pushover results, at each step we can clearly see the displacement occurring in the structure, step by step, how the structure is being pushed. Final step of a proper pushover is the post-analysis, where results are interpreted. Until now, we have only talked about the lateral structural resistance capacity. We didn't mention anything about earthquake demand, what the earthquakes want from the structure. This seismic demand is represented by the seismic response spectrum of the earthquake. Based on the considered seismic code, soil type, corresponding seismic zone, site condition, the adequate elastic response spectrum is defined by the seismic code. Generally, in this seismic response spectrum, we have spectral acceleration plotted versus the vibration period of the structure. This response spectrum represents the seismic demand, what the earthquake wants from the structure. So we have here what the structure can offer, which is the capacity curve, also known as the pushover curve. This represents the resistance, the lateral resistance of the structure. And here we have the seismic demand, what the earthquake wants from the structure. So we need to match between what the structure can offer over here and what the earthquake wants. So we need to know until what extent, what value of displacement will the earthquake push the structure. To do so, we need to find a common point between what the structure can offer and what the earthquake wants. But here it is expressed in force versus displacement, and here it is expressed in spectral acceleration versus period. So we need to find a common reference. This common reference is the ADRS, acceleration displacement response spectrum. So to do so, we need to convert this to spectral acceleration and spectral displacement, and here also we need to convert this to the form of spectral acceleration versus spectral displacement. We will not enter a lot into the conversion details, but once the two of them are conversed, we can try searching for the intersection point, for the point that balances between what the structure can give and what the earthquake wants. This point is called the performance point. It is not directly this intersection point, because here as we have what we call elastic response spectrum, which is the elastic demand curve, but in nonlinear pushover analysis, since the plastic hinges have formed inside of the structure, these plastic hinges will dissipate more energy during earthquake. So for this reason, the elastic demand curve is no longer valid. We need to do many iterations in order to find the correct point where the structural capacity meets the earthquake demand with the corresponding adjusted damping that includes the energy dissipation occurring in the plastic hinges. Now, once performance point has been defined, we know how far the earthquake will push the structure. We push the structure until this displacement step by step. We can visualize where the plastic hinges are forming inside of the structure. We can know the limit state of these plastic hinges, so we can study and see if the plastic deformation is a lot, medium, or small, depending on the performance and importance of this structure. If this is an important structure, we verify that we're respecting the small plastic deformation limit, and so on and so on. We can also identify the critical elements in the structure. For example, if I'm having hinges in the column, this is a bad thing. I don't want it. I want the plastic hinges to form in the beam, so I make proper adjustments. And of course, the behavior coefficient, which is used in the classical linear analysis, can now be validated by doing a pushover analysis. We get the exact behavior coefficient of the structure. Once we have the pushover curve, now we need to determine the performance point. To do so, we need to know the seismic demand. This is generally defined during the model spectral analysis, which is the classical earthquake that you do in advanced design. So we see here, we have here the response spectrum in X direction, defined here, for example, by the Eurocode. So now we have response spectrum, we have pushover curve. We need to determine the performance point. If we go here, we see that in advanced design we have the option to calculate the performance point according to the N2 method of the Eurocode 8 or according to the capacity spectrum method of the ATC40. So if we choose the N2 method, we see that here we have the demand curve, which is the response spectrum, and here the capacity curve, which is the pushover curve, and in the green point is the performance point, which balances between this, what the structure can give and what the earthquake wants. Here we see the coordinates of this of this performance point in spectral coordinates. If we want to get real coordinates, we go here. We see on the base shear versus real displacement of control node, we see the performance point. So, in other words, the earthquake will keep pushing the structure until reaching this displacement over here at the control node level, and we will have this much of base shear on the structure. Also, we can do this calculation using the capacity spectrum method of the ATC40. Here is the performance point. And we can see how step by step the response spectrum, which is the demand curve, is getting smaller, because the more we go forward, the more we have plastic deformation, the more we have energy dissipation in plastic hinges, causes more damping. Also, we can see how step by step hinges are forming. So here we select pushover analysis, and we select hinge status, as we see here, and we can see step by step how hinges are forming. Here, for example, everything is still elastic. We have no plastic hinges occurring. and for example, when we go forward, we see some hinges that have started to form. Here is the hinge status, the hinge limit state, the one we talked about, that this defines the extent of plasticity occurring in the hinge. It's up to the engineer to compare this with the use of the structure. For example, here these yellow ones are occurring in the beam, but for example, they are between damage limitation and significant damage. So we say here, for example, that we have medium plasticity. So if the structure here is intended for a high importance use, this should not be acceptable. Changes should be made in order not to reach this limit of plasticity, for example. And of course, we can see this step by step during the analysis. Also, in the report generation, we can see over here in the results, pushover analysis, we can see plastic hinges and overstrength ratio, which is the behavior coefficient of the element. So if we select, for example, just one element to see this in order not to get a very large report, and we select to see this, we see here how this is the plastic limit of the hinge in this column, and this is step by step the moment inside of the hinge. So you see here everything is still elastic as long as the moment is below this, and once this is reached, you see here, for example, we started to have plastic deformation, and here we have the plastic rotation. And over here we have the behavior coefficient of the corresponding element calculated here. Thank you for your attention. Now it's time for questions. Please, if you have any questions, feel free to ask them in the Q&A section.